The inverse square law is one of the principal aspects of physics, because the world in which we observe things is in 3 dimensions. The world around you is perceived in 3 dimensions. You look up and down, which is 1 dimension. You look left and right, which is another dimension. Finally, you can look up in front of you and behind. These are the 6 directions and 3 physical dimensions which are covered in classical physics. Mathematically, you can extend dimensions to more than 3 by using further axes than x, y and z, but these extra dimensions are difficult to perceive. The second reason why the inverse square law is so important is to do with perspective. No matter the size of an object initially, it will always diminish as you move away from it. The further away you move from the object, the smaller that object becomes. If we take this to its extreme, then we can say that an object viewed at an infinite distance is a point-like object. We live in a 3-dimensional world and can treat objects as point-like objects. This means that we can mathematically work out how radiation emitted from a point-like object behaves in our 3-dimensional space. The conservation of energy says that we cannot lose or gain energy. If we have only one source of radiation in a space, then the radiation energy at the surface of the source will be the same as the energy passing through the surface of any sphere with a radius at the centre of the source. Point sources radiate energy in all directions, so the total radiation at the surface of any sphere of a given radius from the source has the same amount of energy as any other surface of a sphere. The difference is that the concentration of energy within a fixed area on the surface of a given sphere varies with distance from the source. The energy radiated from the source dissipates into the sphere as the sphere encompassing the source gets bigger. The sphere around the source gets bigger as the radius increases. If you wanted to keep the same amount of radiation passing through your area on the surface of your sphere, then your area would have to be equal to the square of the radius of the sphere around your source. In other words, if the total amount of radiation is kept the same, then the area on the surface of the sphere equals the radius of that sphere squared. If you want to keep the area of the square constant and allow the concentration to change, then you rearrange your equation to show that area equals radiation over concentration. As the area on the surface of the sphere is equal to 4 pi r squared, then the concentration or intensity of radiation passing through a fixed area on the surface of a sphere is equal to the original source amount of radiation divided by 4 pi r squared. In practice, the radiation of a gamma source is given as intensity equals a constant value, k, divided by x squared. This is because you have to make adjustments for the equipment you are using to measure the radiation and for the medium in which you are measuring the radiation. These variations are all incorporated in the constant value for your experiment, k. Nevertheless, it can still clearly be shown that the intensity of radiation varies with the inverse square of the distance from point source to detector.